The universe is vast. It is a dark, silent ocean stretching out in every direction. For centuries we have stood on the shore of this cosmic sea. We have looked up at the countless points of light. We have wondered, are we alone? This question is one of the oldest and most profound we can ask. It drives our curiosity. It pushes our technology to its limits. We have built giant telescopes like ears turned to the heavens. We listen for a whisper, a signal, anything that might tell us someone else is out there. It is a search filled with both hope and immense patience. Imagine you are standing on a beach shouting into the wind. You hope someone on a distant island might hear you. The search for extraterrestrial intelligence, or SETI, is much like that. We send out our own messages into the void. Our search for life is not limited to just listening for radio signals. We have another powerful tool, starlight. Every star sings a song, a symphony of light that travels across the galaxy to reach our telescopes. This light tells us a story. It reveals a star's age, its temperature, and what it is made of. It is a cosmic fingerprint, unique and full of information. One of the most powerful ways we study starlight is by watching for shadows. When a planet passes in front of its star, it blocks a tiny fraction of the light. This is called a transit. It causes a small, regular dip in the star's brightness. Think of it like a moth flying in front of a distant streetlight. The light dims for just a moment. The Kepler Space Telescope was a master at this. It stared at one patch of sky for years, watching over 150,000 stars for these telltale flickers of light. These dips in starlight are incredibly predictable. A planet is a round object moving in a regular orbit, so the dimming it causes is smooth and U-shaped. But what happens when we find a star that does not follow the rules? What if its song is strange and discordant? In 2015, astronomers found such a star. It was catalogued as KC 8462852, a fairly ordinary star located about 1,470 light-years away in the constellation Cygnus. But its data was anything but ordinary. It was not singing the familiar tune of a star with orbiting planets. Its light was behaving in a way no one had ever seen before. The star's brightness did not just dip, it plummeted. Normal planets might block 1% of a star's light, but KS 8462852 was experiencing dips that blocked up to 22% of its light. That would require an object of enormous size, far larger than any known planet. Furthermore, the dips were not regular. They happened at random intervals and lasted for different amounts of time. Scientists were stumped. They checked the data. They checked the telescope. Everything was working correctly. The star itself seemed normal. The Kepler Space Telescope was a fire hose of data. The sheer volume of this information was too much for professional astronomers to handle alone, so they turned to the public for help, launching a project called Planet Hunters. These citizen scientists became digital explorers, charting unknown corners of the cosmic ocean. They would look at light curves, which are graphs showing a star's brightness over time. In 2011, several of these volunteers started flagging one particular star, KIC 8462852. The light curve for this star made no sense. It didn't have the neat, repeating dips of a planet. Instead, it looked like a chaotic scribble, a line that dropped suddenly and unpredictably. The volunteers who flagged the star were intrigued. This discovery highlights a beautiful aspect of modern science. It was not a famous astronomer in a lonely observatory who first noticed this cosmic puzzle. It was a group of ordinary people driven by passion and curiosity who made the initial find. Their fresh eyes, unburdened by preconceived notions of what a star should look like, were perfectly suited to spot something truly new. The story of Tabby's star began not with a bang, but with a collective "huh" from a worldwide team of volunteers. When the professional astronomers, led by Tabby Boyajian at Yale University, took a closer look, they were just as baffled as the citizen scientists. The star itself, KIC 8462852, seemed perfectly normal. It was an F-type main-sequence star, a little bit bigger and brighter than our own sun. It was located in the constellation Cygnus, the Swan, about 1,470 light-years from Earth. The team's first job was to be skeptical. They had to rule out every possible error. Could the strange signal be coming from the Kepler telescope itself? They checked the instrument's logs and performance records. Everything was fine. Could the data have been corrupted during its long journey back to Earth? They cross-referenced different data sets. The signal was consistent. Every mundane explanation they tested led to a dead end. The Kepler data showed two major dimming events that stood out. The first, around day 800 of the Kepler mission, was a single sharp dip that blocked about 15% of the star's light. Then, around day 1500, a whole series of bizarre dips occurred over several weeks. The light from the star flickered and plunged wildly. At its lowest point during this period, the star's brightness dropped by an astonishing 22%. Let's take a moment to truly appreciate how strange this data was. Imagine you are watching a lighthouse from a boat at sea. You know its light is supposed to be steady and constant. Suddenly it flickers. This is what astronomers saw when they looked at the light curve for Tabby's star. It was not the gentle, symmetric U-shape of a planet. It was a jagged, asymmetrical mess. The first major dip, the 15% drop, was strange enough on its own. It was not smooth. This asymmetry told scientists that whatever was blocking the light was not a sphere like a planet. It had an irregular shape, perhaps with a leading edge and a long, trailing tail of debris. This was the first clue that they were not dealing with a simple, solid object. It was a complex structure, or perhaps a cloud of them, that was casting this strange shadow across interstellar space. The second series of events, the cluster of dips around day 1500, was even more baffling. It lasted for nearly 100 days. During this time, the star's light plunged multiple times in quick succession. The pattern was chaotic, with no obvious repetition or rhythm. It looked like a whole swarm of objects of varying sizes and shapes was passing in front of the star. It was more like a cosmic traffic jam, a disordered and clumpy cloud of material. Faced with such a bizarre signal, the first instinct of any good scientist is not to jump to wild conclusions, but to rigorously test every mundane possibility. The team led by Tabitha Boyajian began a systematic process of elimination. The first and most obvious culprit for strange stellar signals is the star itself. However, Tabby's star showed no signs of being a variable star. Its color and temperature remained constant, even as its brightness plummeted. The next logical suspect was a disk of dust and gas. Young stars are often surrounded by protoplanetary disks, where planets are born, but Tabby's star was not young. It had long passed its turbulent youth. Furthermore, such disks emit a telltale glow in infrared light, because the dust is warmed by the star. When astronomers looked for this excess infrared radiation, they found none. There was no vast warm disk of dust. What about a catastrophic collision? Perhaps two planets in the system had recently smashed into each other, creating a massive field of debris. However, such an event would create a huge amount of fine-grained dust, which would again produce a strong infrared signal. Finally, the team considered a massive swarm of comets. This became the leading conventional hypothesis. Perhaps a passing star had gravitationally disturbed a vast cloud of comets, sending a huge number of them plunging toward the star. When Tabitha Boyajian and her team finally published their paper in 2015, the scientific community, and honestly, the whole world, took notice. The paper was cautious, methodically ruling out one explanation after another, but its conclusion was electrifying. They had a mystery on their hands. The star's light curve was so strange that Boyajian and her colleagues couldn't find a natural phenomenon that fit the data. In an early draft of their paper, they had a section titled, "What the heck?" which perfectly captured the feeling of bewilderment that this star produced. The star was soon nicknamed Tabby's star, but it also gained another, more provocative name, the WTF star. The reaction was immediate and widespread. Astronomers around the globe were fascinated. Here was a genuine cosmic puzzle, a signal that did not conform to any known astrophysical model. It was a challenge to our understanding of how star systems behave. The data from the Kepler telescope was unambiguous, yet its meaning was completely opaque. The public was just as captivated. The story quickly spread beyond scientific journals and into the mainstream media. The idea of a star that flickered and dimmed for no apparent reason ignited the popular imagination. It tapped into that deep primal curiosity about the cosmos and our place within it. Could this be it? Could this be the sign we had been searching for? The cosmic detective story of Tabby's star had officially begun, and everyone was invited to follow the clues. With all the conventional explanations looking increasingly shaky, astronomers found themselves in a strange and exciting place. The comet swarm theory required an unbelievable coincidence. The planetary collision theory did not fit the lack of infrared heat. Science works by testing hypotheses, and one by one the natural hypotheses were failing the tests. When you have eliminated the probable, you must start to consider the improbable. This is a line of reasoning famously captured by the fictional detective Sherlock Holmes. This led some astronomers, like Jason Wright from Penn State University, to cautiously whisper a truly extraordinary idea. What if it wasn't nature at all? What if it was technology? For the mystery of Tabby's star, the improbable was the idea of an alien civilization. It is a huge leap, one that scientists are very reluctant to make. The history of astronomy is filled with mysteries that seemed strange at first, but were later explained by natural causes. But this time, the data was so stubbornly weird that the alien hypothesis had to be put on the table. The idea was not that aliens were trying to send us a message. It was more subtle than that. The hypothesis suggested that the strange dimming events might be the unintentional byproducts of a massive engineering project. An advanced civilization would have colossal energy needs, far beyond what could be gathered on a single planet. To power their world, they might begin to build enormous structures in space to capture the energy directly from their star. The concept of an alien megastructure is most famously associated with one man, the physicist and philosopher Freeman Dyson. In 1960, Dyson thought about the long-term future of any technological civilization. He reasoned that as a civilization grows, its demand for energy will inevitably grow with it. Eventually, the energy available on its home planet will not be enough. The ultimate source of power in any solar system is its central star. A truly advanced civilization, he proposed, would learn to harvest this energy directly. They would begin to build a vast collection of solar collectors and habitats that would eventually enclose their entire star, capturing every last bit of its energy output. This hypothetical megastructure became known as a Dyson sphere. It is not necessarily a solid, rigid shell, which would be gravitationally unstable. Instead, most envision it as a Dyson swarm, a dense, independent fleet of orbiting structures. Such a structure would be one of the most powerful signs of intelligent life we could hope to find. A completed Dyson sphere would block all the visible light from the star, making the star seem to disappear. However, it would have to radiate the waste heat away as low-temperature infrared radiation. Freeman Dyson himself urged astronomers to search for these objects, these artificial infrared sources. The search for extraterrestrial intelligence has traditionally focused on listening for radio signals, but Dyson argued that we should also be looking for the physical evidence of cosmic engineering projects. The idea of a Dyson swarm provided a tantalizingly neat explanation for the strange behavior of Tabby's star. It just seemed to tick all the boxes, really. The deep, irregular dips in starlight could be caused by large, non-spherical pieces of a megastructure passing in front of the star. If a civilization were in the process of building a Dyson swarm, they'd have many massive construction components and partially completed habitats in orbit. These would not be uniform, and they wouldn't be in a simple, periodic orbit. This could create exactly the kind of chaotic, jagged light curve that Kepler observed. The swarm of structures would cast a complex shadow, just like the one we saw. This hypothesis could also potentially explain the mysterious long-term dimming. If a civilization is actively building a Dyson swarm, they'd be constantly adding new structures to the cloud. Over the course of a century, the number of orbiting objects would increase, blocking more and more of the starlight. The short-term dips and the long-term fading were two separate puzzles, but the megastructure hypothesis could potentially solve both of them with a single audacious idea. We were watching a Dyson swarm being built piece by piece. As the famous astronomer Carl Sagan often said, extraordinary claims require extraordinary evidence. The idea that KIC 8462852 was surrounded by an alien megastructure was perhaps the most extraordinary claim in modern astronomy. While it seemed to fit the bizarre observations surprisingly well, scientists could not simply accept it. They had to test it. The alien megastructure hypothesis was thrilling. It really captured the imagination of the world. But in science, Imagination is only the first step. The real work is in the rigorous, patient testing of ideas. While the media buzzed with talk of Dyson spheres, the scientific community got back to work. They knew they had to give natural explanations another, harder look. The principle of Occam's razor guides this process. It says that the simplest explanation is usually the best one, and an explanation involving a completely unknown alien civilization is anything but simple. Astronomers returned to the drawing board. They began to think more creatively about what natural phenomena could be at play. What if a single gigantic supercomet had broken apart after straying too close to the star? This disintegrating planetesimal idea suggested that a massive icy body had been torn to shreds. This scenario had some advantages. A single catastrophic event could explain why the dimming was so sudden and non-repeating. The breakup of a massive body would create a chaotic swarm of irregularly shaped fragments, which could produce the complex, jagged light curve that Kepler saw. Other ideas were also floated, each trying to solve a piece of the puzzle. Perhaps Tabby's star is currently undergoing a late heavy bombardment, with a massive swarm of comets or asteroids being gravitationally disturbed and sent careening through the inner system. These bodies would constantly collide and break apart, generating a continuous supply of fresh dust that replenishes the cloud as fast as the star's light can blow it away. This ongoing planetary demolition derby could potentially explain both the short dips and the long-term dimming. With the Kepler mission having moved on to observe other parts of the sky, astronomers were left in a difficult position. The scientific community knew they could not let this mystery go unsolved. They needed more data. Tabitha Boyajian launched a Kickstarter campaign to raise money for dedicated telescope time. The public response was overwhelming, raising over $100,000. This allowed her and her team to buy time on a global network of private observatories. Amateur and professional astronomers around the world pointed their telescopes at KIC 8462852. For about 2 years, the star remained quiet. The long watch continued, a patient vigil across continents. Then, in May 2017, it happened. The alerts went out across the network. The star is dipping. This time, when the brightness began to fade, scientists were ready. They aimed a host of powerful instruments at the star, capturing the event not just in visible light, but across the entire spectrum, from X-rays to radio waves. This was the crucial moment. By analyzing the colors of the starlight as it passed through the obscuring material, they could finally learn what it was made of. This new data was a game changer. The observations showed that blue light was being blocked more than red light. This is a telltale signature of tiny particles, specifically dust. Large, solid objects like planets or alien megastructures would block all colors of light equally. But a cloud of fine dust particles scatters blue light more effectively, letting more red light pass through. The biggest breakthrough in the case came when the star started dimming again in 2017. Armed with the funds from the Kickstarter campaign and a global network of telescopes, they watched the event unfold across the entire spectrum of light. Think about a sunset on Earth. As the sun's light travels through more of the atmosphere, tiny air molecules scatter the blue light away, leaving the red and orange light to reach our eyes. The material around Tabby's star was doing the same thing. It was acting like a cosmic smokescreen. This was a major blow to the alien megastructure hypothesis. A large, solid object, like a solar panel or a habitat, would be opaque. It would block all colors of light equally. If you hold your hand up to a light bulb, it doesn't just block the blue light, it blocks everything. But the shadow cast by the stuff around Tabby's star was reddish. This strongly suggested the blocking material was not made of massive, solid structures, but rather a vast, translucent cloud of fine dust. The culprit was not a fleet of alien spaceships, but something much more mundane, a whole lot of cosmic dust. This discovery shifted the entire focus of the investigation. The question was no longer, is it aliens? But where did all this dust come from? The dust cloud had to be enormous to cause a 22% dip in starlight, yet it couldn't be primordial dust left over from the star's formation. It also couldn't have been there for long, because the star's radiation would have blown such fine dust away in a relatively short time. The dust had to be new. It had to be freshly produced. The mystery was still alive and well, but it now had a new central character, a vast, inexplicable cloud of dust. As of today, in 2024, the mystery of KIC 8462852 is not fully resolved. There is no single, universally accepted explanation for all of its strange behaviors. The scientific community has largely moved on from the alien megastructure hypothesis, with the evidence for dust being quite strong. However, the leading natural explanations, such as a disintegrating moon or a massive cometary swarm, still feel incomplete. They are plausible stories, but they require events of such a rare and monumental scale that they stretch the boundaries of what we consider likely. The science remains unsettled, leaving the door open for new ideas and future discoveries. The ongoing study of Tabby's star continues to rely on patient observation. Global networks of telescopes are still keeping a watchful eye on the star, ready to capture any new dimming events in unprecedented detail. Scientists are also using powerful new instruments like the James Webb Space Telescope to probe the system for faint infrared glows that might have been missed before, hoping to find the smoking gun that points to the dust's true origin. What we have learned so far is a lesson in scientific humility. Tabby's star has shown us that the universe is far stranger and more complex than we imagined. It has challenged our standard models of how star systems should behave after billions of years of evolution. Ultimately, the story of Tabby's star is a perfect example of science in action. It is a tale of curiosity, collaboration, and rigorous debate. It began with citizen scientists spotting an anomaly, blossomed into a global mystery that captivated the public, and evolved into a deep technical puzzle. In the end, what is the legacy of Tabby's star? It is a story that began with a strange flicker of light and spiraled into a global sensation, igniting one of the most exciting astronomical debates of the 21st century. The tale took us on a wild journey, from the patient work of citizen scientists to the audacious hypothesis of alien megastructures, and back to the intricate forensics of cosmic dust. While we may not have found definitive proof of an extraterrestrial civilization, the search for an answer has given us something just as profound. It has given us a masterclass in the scientific method, and a powerful reminder of why we look to the stars in the first place, for the sheer wonder of the unknown. Good science is not about having all the answers. It is about asking the right questions. It is about embracing uncertainty and having the courage to say, "We don't know." The mystery of Tabby's star created a space for this kind of intellectual humility and boundless curiosity. It forced astronomers to question their fundamental assumptions about how star systems work. It pushed them to devise new theories, new observational techniques, and new ways of collaborating across the globe. The story also revealed the incredible power of the human imagination. The alien megastructure hypothesis, while now considered unlikely, was not a failure of science. It was an essential part of the process. It was an act of disciplined imagination, taking an extraordinary observation and asking what extraordinary cause it might have. This willingness to entertain bold, out-there ideas, even if they are ultimately proven wrong, is crucial. It stretches the boundaries of our thinking and ensures that we do not prematurely close the door on a universe that has repeatedly proven to be stranger and more wonderful than we could have ever predicted. Ultimately, mysteries like the one surrounding KIC 8462852 are gifts to science. They are the anomalies, the discordant notes in the cosmic symphony that signal the edge of our knowledge. They challenge us to be better detectives, to build better tools, and to think more deeply about the cosmos. The star's strange behavior has already inspired dozens of scientific papers and countless hours of telescope time, enriching our understanding of stellar physics and the chaotic dynamics of planetary systems. The puzzle may not be fully solved, but the quest to understand it has already made us smarter, more capable, and more curious explorers of the universe. The saga of Tabby's star has reshaped our search for life in the universe. For decades, SETI was dominated by listening for radio signals, but Tabby's star taught us to broaden our horizons. We should be searching for technosignatures, the large-scale, unintended byproducts of an advanced civilization. So, are we alone? Tabby's star did not answer that ultimate question, but it did something just as important. It reignited our collective imagination and sharpened our tools for the search. The hunt goes on, now broader, smarter, and more hopeful than ever before. As we continue to watch, to listen, and to wonder, we do so with a renewed sense of awe. The cosmos is not a static, predictable machine. It is a dynamic and evolving stage of immense complexity. And somewhere out there, among the countless points of light, new mysteries are waiting to be discovered. The star remains an enigma, a beacon of the unknown, reminding us that there are still great wonders out there, waiting to be discovered. The mystery continues, and so does our search for answers in the vast cosmic ocean.